Hello, everyone. Whoa, that was too loud. Hi. Thanks for being here. I hope you're having a good GDC. We're going to talk today about RTX technologies coming to Unreal Engine 5. We have new technologies that are out this week, as well as more on the way. And I want to talk about them in the context of some very complex scenes we made recently. Namely the Zorah project and amusement park. Both of these scenes take advantage of these technologies in different ways. So here's our agenda. We are going to first talk about the new and refreshed RTX technology that we just released. This involves stuff like real-time path tracing, neural rendering, and we want to make this as easy for you as possible to make use of in your own work. Then I'll talk a little bit about what it's like to make art for this technology and what we learned about it. Our high-level goal always is to make it really easy for you to just use the technology and go and not have to make a lot of modifications to what you're doing. That said, there are details to consider, things to watch out for, and I'll get into that. Especially, there's some interesting topics around authoring textures and materials and things like that. Finally, I'll spend a little bit of time at the end talking about scalability as it relates to RTX technology and our software releases, what we have out this week. We get asked a lot about how do I design my title to use, like, say, real-time path tracing at the high end, and then make sure I can still, make lower-end SKUs work or other platforms and things like that. So I can suggest some ideas that I hope will be helpful to you in that sort of development. There's going to be a lot of pretty screenshots in this one. This is the Zorah project. It's an everything project. It's designed to take advantage of everything that we're basically currently doing. As far as specific technologies go, we're going to talk about RTXDI, DLSS 4, and RTX mega geometry. But in the interest of time, I'm going to limit it to these three. There's a lot more to talk about, but these are probably the most relevant because they're out this week, so you can make use of them immediately. And I'm going to try to talk about them in a practical context. So we're going to look at, CVARs and project settings and things like that. So it's not just pie in the sky stuff. This is actually usable. Oh, sorry. I went one too far. Okay, so all of these technologies, we work on them in what we call the NvRTX branch. It's just NVIDIA optimized ray tracing and path tracing branch. The key feature, or at least one of the key features of the NvRTX branch, is RTXDI, and it's short for RTX Dynamic Illumination, and this is really just our acronym for real-time path tracing. So you can call it real-time path tracing, RTXDI. It's the same thing. There's other names it goes by. We're going to get into that. The technical terms are either sampled lighting, you'll see that referenced in code, or ReSTIR. And like I said, we'll get into these topics. I'm not trying to confuse you by saying there's lots of different ways to describe real-time path tracing. It's just that it's had a complex development, I guess. So yeah, RTXDI is one of the key features of the branch, and it has the capability now, this is just released in the past month, for full real-time path tracing. And what I mean by that is you can use RTXDI to do your direct lighting, your indirect lighting, your GI, and your reflections. So you can do full mirror quality reflections in real time, and everything that you would see in direct rendering that the path tracer would pick up would be represented in that mirror. This scene here is the amusement park, and it's showing one of the specific features of RTXDI, which is very high light counts. I'm sure if you're using megalights, you're familiar with this from that perspective, but it's very similar in that respect. One of the key features of real-time path tracing is flattened lighting costs. So you can do 100 lights, 1,000 lights. It's all roughly the same cost. And the amusement park here, this scene should be out this week, and it uses 1,000 shadow casting path trace lights. And a lot of them are physically animated, moving through the world. So you'll see a lot of shadow activity and complex interactions that you wouldn't get otherwise.
Good.
This is how you enable RTXDI in the branch. When you're using NvRTX, we try to make this really simple. The technology has matured quite a bit. We've been working on it for years. So in the project settings, it's pretty direct. You just go to the rendering tab, and let me get my virtual laser pointer here. There's an option here to turn on RTXDI, ray traced sampled lighting. And when you do that, you can see that there's actually a couple other features we're going to talk about, transparent shadows. But when you do that, as long as you have your project set up for ray tracing, so DX12 and hardware ray tracing are enabled, then that's it. Now you have access to RTXDI, and you're good to go. So, we just talked about high light counts. That's important, but that's not all RTXDI does. It actually gives you some new features. I'll step through those so we can understand it better. It's worth noting that all light types are supported with RTXDI. So obviously, yes, all your local lights are capable of being path traced, but we also can path trace a directional light and a skylight. There's a technical note on the skylight. We're not currently path tracing the indirect illumination portion of the skylight. You can do direct lighting off the skylight path traced. This is should be part of a future update, but that's where we're at with this progress. Oh, and another screenshot of Zorah. Zorah makes use of every kind of light there is, and yeah, they're all path trace lights. Yes. Emissive lighting is one of the neat tricks you can do with real-time path tracing. So on the left is, well, first off, this is just a little test scene. Very, very simple. There's no actor lights in the scene at all. It's just meshes with an oddly shaped emissive mesh, this curlicue thing. And so on the left, we have what hardware ray trace lumen does with that. And on the right is the path traced version. So you can see that real-time path tracing has the ability to work on top of lumen. So you set your project up for lumen, and then with a checkbox, you can just enable real-time path tracing on top of that. So it gives you a quality boost, and it's able to basically treat every single emissive triangle as an individual light source. So you get highly accurate lighting off of emissive meshes. Now, this is, I will caution this a little bit. I know this looks really good in a screenshot. The technology still fundamentally wants actor lights in order to sort of ground the scene. So you can light your scene entirely with emissives, but you probably have to crank up your sampling and your candidates a little bit, and it can start to get expensive. So if your target is 60 FPS broad support, this isn't it. But if you're interested in cutting edge features, or you just want to try to light your scene entirely through physical materials, you can do that. Transparent colored shadows are also on display in the Zorah and amusement park projects. This is really powerful stuff. We do full light transport through your material. So it'll look at the color value of your material, the translucency value, and read that and do path trace shadows appropriately. In fact, in Zorah here you can see that it even works with fog shadows. So you can see it's kind of colorized the fog streamers as they come down to the ground, reading the material and everything. So that all works. Finally, path trace Niagara lights. So this is an ember effect. It's just little fire particles, and just sprites. But each sprite is generating a light source, and with RTXDI, you can turn it on for that effect. You can do it individually, for individual effects, or globally for everything, and have shadow casting lights from your Niagara particle systems. There's really no limit to that. I mean, you get your full, direct and indirect lighting. The cool thing about this, from a performance standpoint, is Niagara lights are processed entirely on the GPU. So the more of this you can do, especially from an animated moving shadow casting light source, the more performant your scene gets. If you can imagine, RTXDI we don't know exactly what the upper bound threshold is for light actors or how far you can really go with it. But if you can imagine, if you do, 1,000, 2,000, 10,000 lights, shadow casting, that number would be 10 times higher if they were all Niagara lights. So the more of this you can do, the more performance you get. Okay, as I said, RTXDI works with Lumen. The implementation is pretty straightforward. Once you turn it on in your project settings, that gives you can imagine there's different levels to RTXDI. The first level is just turning it on in the project settings. That makes it so that all your lights at that point have the capability of becoming path trace lights. And by default, they will now cast path trace direct shadows. So, and like I said, the number one feature with that is, flattening your lighting costs, performance. So it doesn't matter how many lights you put in the scene, you get very good performance with very high light counts. But the next level of that is to go to your post-process volume and turn on, use RTXDI indirect lighting in Lumen, which you can see here. So when you turn that on, now you're enhancing Lumen with path traced global illumination. And reflections go up a little bit in quality. You're not doing mirror lighting, you're not doing full path tracing yet, but you're doing the next step up. Yeah, so that's implementation is pretty straightforward. This is also part of the post-process volume. Most of the settings you can get into CVARs, you can fiddle with things that way. There's a ton of CVARs, and we try our best to document them all. But we have recently moved a lot of this to, the post-process volume, so you can go to the sample lighting tab and modify probably 90% of your needs right here and not have to fiddle with CVARs. I'm not going to go through all of these individually. There's a lot, but the key ones to know, if you're worried about what's going to affect your performance, what's going to drag performance down, anything with candidates, visibility tests, samples, or bounces in the name is going to have an impact on performance. So yeah, the more you turn those on, the more you crank them up. Basically, the higher quality but slower the path tracer is going to get. Everything else, like boiling filter strength or anything to do with history length or anything like that, are preferences. So that's just fine tuning for your scene. You can plug in different values, higher numbers, lower numbers. It's not going to dramatically affect the performance of your scene, and you can, it might help tweak out the quality a little bit. So those are just content tweaks. Okay, so I've described turning on direct illumination with path tracing and then global illumination with path tracing. In order to go all the way to full real-time path tracing, you do need to enter a console command. That's because path tracing, full path tracing is brand new. We just got it in, like I said, about a month ago. So there's a console command here. You can see it's indirect mode 2 that you'd want enabled. Mode 1 is the default. Mode 1 is the GI portion of RTXDI. So mode 2 takes it to full path tracing. And I'll show you visually what that means in a minute. Simple mode 1 is, this is a temporary measure. I'll be completely honest about this. This is something we're doing in the moment for now because ReSTIR, RTXDI with full path tracing is so new that we needed a way to help stabilize the signal so that you don't get a lot of noise or crawling when you're moving. So simple mode 1, the default is 0, but turn that on. If you're using full path tracing, it'll help to keep your scene looking better. And for your awareness, there are different indirect modes to try. 0 is just turning GI and path tracing completely off. 3 is a debug mode. It's actually like a full unbiased path tracer, R path tracer, put into Unreal. You can always validate, like if you're in mode 2 and you're looking at your path trace scene, you can always validate what you're seeing by looking at Unreal 5's built-in offline path tracer. You can just go there, check it, make sure that it's doing the right thing. But we also have our own path tracers, and that's mode 3. So this isn't really meant to be like shipping ready or production ready, but it is something that you can use to check mode 2 if you just see any kind of inconsistency or something that you don't expect. Okay, I think I kind of hinted at this before. ReSTIR is the core algorithm. So we call it RTXDI, or like I said, real-time path tracing, sampled lighting, goes by many different names. ReSTIR is the core algorithm. That's what does your actual path tracing work. You can see what ReSTIR stands for. It's a nice mouthful, reservoir spatio-temporal importance resampling. The bottom line, I don't want to get too much into this because we have, if you're interested in that, there's white papers on the NVIDIA website. You can dive deep into it. But the important thing here is that, like I said, it does your path trace direct lighting, your indirect lighting, and full reflections. So what I can show you here in this example scene is how you might scale that in depending on the kind of details that are important to you. So first off, like I said, when you just enable it in the project, that gives you sort of the first level of ReSTIR, which is the direct illumination portion. So here I have it's a kind of a simple scene, but it's just this robot character standing in front of a full mirror. And it's a lumen-lit scene. There's nanite geometry everywhere. And you can see some of the problems. This is we're using ReSTIR-DI, so the direct shadow, the direct lighting, it's actually from a sunlight, is casting path trace shadow down here. That's nice, but we haven't modified the GI at all, so we're just using lumen at this point with screen traces turned on, and you can see the problems in a mirror. This is sort of the difference between a ray traced reflection and a path traced reflection. So at this point, we're missing information. If you look at the character, the front of him is black. Anything that's in indirect lighting isn't picked up by the ray tracer, so it's not fully represented. Now, if I turn on ReSTIR GI, which is done under global illumination, I showed you before, we've improved the GI signal. I'll flip back so you can see this. The GI has gained more energy. You're able to do more bounces when ReSTIR GI is activated. It also improves specular and reflections a little bit, not mirror reflections, but rougher reflections. So typically anything, it uses the roughness control in the post-process volume. The default's 0.4. And what that means is anything under that is going to use lumen. Anything above that is going to use path tracing. So you get path traced specular quality and rough reflections are improved. So those things account for some of the increased energy that's going on here. But you can see that ReSTIR GI doesn't solve the reflection issue. Not fully, anyway. So here we are, the same scene, and now we're using full path tracing. So I'll just flip back and forth a little bit. You can see that the character looks pretty good, and the GI changed a little bit. Maybe the specular highlights changed a little bit. There are subtle differences between the ReSTIR GI algorithm and ReSTIR PT. ReSTIR PT is more current, and technically it's got a higher max bounce count. I think it can handle up to 7 bounces in the scene. But the main difference is in the reflections. I mean, really, if you're using ReSTIR GI and you're not doing any mirror reflections in your scene, you don't have to change anything. But if your ambition is to do something like that, then you'd want to go to ReSTIR PT. And you see that the indirect lighting for the character is fully represented in the reflection. In fact, if you took the camera and put it right up against that mirror, it would almost look like direct rendering. It'd be really hard to tell the difference. So ReSTIR PT is very powerful. And that's why we refer to it as full path tracing. We're not path tracing every effect. We're not doing translucency and certain other things. But like I said, reflections, indirect lighting, and direct lighting they should match the path tracer or any path traced quality effect. Okay. Next technology item, switching gears here completely. DLSS 4. We have the latest out today in Unreal Engine. It came out, I think, last month. But this is fully up to date in NvRTX. It's also out as plugin. The key new features for DLSS 4 are ray reconstruction and multi-frame generation. So you have access to those today. But everything across the board is pretty updated because the transformer model is now part of this. And you can select that. You can go into your preferences and choose different models if you want. But the point is that the transformer model is now part of DLSS 4. So it improves super resolution quality. It improves ray reconstruction, frame generation. There's dramatic quality and performance differences across the board. You can see some of how ray reconstruction really improves reflection quality in cyberpunk path traced mode. These images are recorded at 50% quarter res input resolution. So it's able to reconstruct neurally the path traced image incredibly well. I mean, ray reconstruction was designed for real-time path tracing. It was trained on it and it's designed for it. So if you're doing any kind of advanced ray tracing or heavy ray tracing effects or path tracing, I would encourage you to use ray reconstruction as your denoiser. And here you can see in Unreal how we try to make it really, really simple to implement full DLSS 4. In fact, that's all you have to do right there, those 3 blueprint scripts. Turn them all on, link them up, and if you just wanted to rapidly prototype full DLSS 4, it's in those 3 right there. There's a lot of things here: fine details, high contrast details, thin meshes, all the small details that in the past DLSS 1 would have probably failed on, especially at a 50% input resolution, that are, they seem to be very resolved under DLSS 4. So the quality is dramatically improved. Yeah, final new feature that I'm going to talk about will be RTX mega geometry. We have this out as of this week. Mega geometry is very straightforward. It does one thing and one thing only. It takes your nanite geometry and allows you to ray trace it and path trace it at full resolution. So it doesn't matter how many triangles it is or anything. You just you're all set to go to fully path traced your nanite. I would caution a little bit with this technology. We've released it in what we call an experimental state. It's kind of a pre-beta. We don't want to sit on it. We want to get it into your hands so you can start to use it. So right now it's activated through CVARs. We would like to make this better over time, but this is the first stop, if you will. You enable it really easily. You do this the CVAR here, R nanite ray tracing equals 1. And read-only means you just have to enable it outside the editor, right? So set it up in your default engine INI, for example. Once you do that, Mega Geometry creates a new acceleration structure for your nanite. It's called the CLAS, the cluster level acceleration structure. And it just takes all of your nanite geometry, whatever you have in your scene, and puts it into that buffer so that you're now able to path trace everything in your scene that is recognizable by hardware ray tracing, which these days is just about everything. This is how you tweak your settings for it currently. Again, experimental release. That's what we're calling it. Like I said, it's a pre-beta state. But what you need to do in order to make use of it is set your memory budgets. You can do this by going into the editor and typing this command, and that'll, as you can see in the editor video here, there's some debug information about how much memory is currently being used. So you type this stat show command equals 1, and then the numbers will fluctuate as you fly around the level. What you're looking for is hotspots. You want to find your heaviest spot, and then plug those numbers into your budgets, these 4 values down here, and just make them part of your default engine. Again, I know I'm going to sound like a broken record. We want to make this a lot more easier to use in the future. It would be nice if this was automatic. So we're really thinking about that. But yeah, we don't want to, sit around trying to make it perfect. We want to get it to you so you can see how it benefits you. Okay, completely switching gears. I'm going to talk about Zorah art. This stuff, mainly in the context of texture authoring and modeling. We learned a lot making Zorah. Amusement Park too, but Zorah is, like I said, it's the everything project. It's making extensive use of technology in a way we've never done before. So there's a lot that we learned about this, and I just want to impart some of that information to you. First off, some fun facts made by a team of about 20 artists at NVIDIA. The core art team was more like 15 people, but we had various people coming in and out at different points, handling different technical art needs and whatnot. Hundreds of 8K textures. It's just chock full of them. It's almost hard to characterize how many are there. Lots of very high poly meshes. Over 321 million plus triangle meshes, over 10 million plus triangle meshes, over 1,000 unique meshes. The highest triangle mesh was 32 million. Someone can correct me if I'm wrong, but I believe that's if you look at some of the screenshots of Zorah, there's a dome in the distance. I believe that's what that is. Most meshes are well under that, but that one was sort of the Big Bertha. And like I said, it's designed to be an everything project. It's using every technology we have, plus all the latest Unreal 5 stuff. Runtime triangles, 800 million. I'm told that there are some locations where that number might be as high as 3 billion. So we're really pushing what we could do with geometry in this scene, to say the least. Target hardware is any RTX GPU with enough VRAM. We're saying 11 gigabytes if you want to load the scene in the editor. That's for the project files. And like I said, those should be out this week. I think they're out now. For a shipping build, a compiled build, it doesn't quite need that much. It's more like 9 to 10. But the thing that's interesting about that is this is making extensive use of megageometry. And megageometry is not final in terms of performance or memory. So you can imagine with more optimization, the scene could work on an 8 gigabyte card. But yeah, currently the technology is not there. Just know that megageometry is currently using more memory than it probably will in the end, although, it's hard to characterize that. I won't say too much about texture authoring, well, not a ton here, but just to say that we made use of virtual textures and UDIMs extensively. I think that's logical for a project like this. So I'm sure this won't come as too much of a surprise. Long term, we would love to, make use of neural texture compression. That is an upcoming technology we have. But for now, especially when you're dealing with, resolutions of this size, the, details of this level, UDIMs and virtual textures, I'd say really saved us. Now, there are some considerations when authoring textures for path tracing when it comes to ambient occlusion. There's so much to talk about with this. Ambient occlusion, first off, anytime you use ReSTIR GI or PT, ambient occlusion as a real-time effect no longer exists. We're not doing screen space ambient occlusion, DFAO, those sorts of things. What used to be ambient occlusion is now your GI. So all of your indirect lighting, your shadows, those sorts of things that we would approximate with ambient occlusion in the past are now being done in a path traced way. So I guess that's point number one. Point number two is that ambient occlusion maps aren't used when real-time path tracing is active. So that's when ReSTIR GI or PT is active. Because if we did that, we'd be doubling up ambient shadows. The path tracer is able, on a per pixel level, to capture all those tiny details. Here we have this is a close-up of a tree with vines growing all over it, and we're like in shadow or lighting only mode. And you can see there's a lot of subtle shadow effects and detail going on there. So I guess my point with this is that if you're making ambient occlusion maps and you want to have that broad scaling across, multiple levels of hardware and hardware generations, ambient occlusion maps make sense still, especially if you're, like I said, you want to be compatible on a lower end, you want Lumen to run on a 20 series. You don't want to do path tracing on that, but then at the 50 series, you would, you switch to path tracing. The ambient occlusion maps are automatically turned off in code. So this is an interesting topic. It's a change in what people are used to and how they're thinking about these subjects. So there could be a lot to discuss with this. This was our hardware, not that literal machine, but these were the specs for all the artist machines within NVIDIA. I was really curious about this one. Every artist machine had 128 gigs of RAM. My work machine has 64 gigs, so to me that was blowing my mind. They found it completely necessary. Like if you were working on meshes of 20 million plus polygons, you just couldn't, or consistent 8K textures across the board. There's just no way you could deal with anything less than 128 gigs in a production environment. So very beefy machines were used. I wanted to list out all the software that we used, just so you got a sense of sort of like what went right and a little bit what went wrong for us. When it came to, I'll get more into this in the next slide, but when it came to auto unwraps, Substance Painter was the MVP for us. There's no Adobe promotion here whatsoever. It just internally, this was good for us. It was the best tool for doing extremely high poly unwraps. So good on them for doing a good job with that. RISM UV was like second place for that, but like I said, these were the tools we were using. So despite all these insanely high targets for Zorah, we still found it very important to be judicial about how we're using polygons as much as we possibly could, mainly because there are pain points. Even with really beefy hardware, you still have to worry about the importing, the exporting, the UV map generation. Those things could take minutes, tens of minutes, hours sometimes, depending on what you're doing. So we developed some rules internally. We focused on the silhouette of meshes in order to, just go after those details. Well, we tried to stay away from needless subdivision. If it didn't contribute to the shading or the silhouette of what you were seeing in the scene, we didn't throw extra polygons just to throw extra polygons at it. But still, I mean, it's real interesting because if you look at the wireframe, the nanite wireframe on Zorah with the fully considered, meshes fully represented, where generally, aside from not doing unnecessary subdivision, generally the complexity is such that we're kind of following the standards that Epic has set forth in the sense that you're generally rendering one triangle per pixel. So the meshes are insanely dense. That's sort of what's expected with nanite, and that's what we're doing here. We still would run into, like I said, pain points when it came to import, export, UV generation. So our advice internally, and we would extend to you if you're dealing with if you're doing this kind of work. I'm sure you're probably aware of it already, but we found it beneficial to do unwraps on low poly meshes whenever possible, and sort of if you can do your subdivide later and maybe displacement map it in order to avoid unwrapping a high poly mesh. That's beneficial, but that's not always possible. A lot of times it's not possible. So then the next line of defense was breaking up meshes into smaller parts and unwrapping them, a bit at a time. But when that's not possible, beefy hardware, and that's sort of where we landed. Substance painter was a big lifesaver for us. Okay, final subject. I want to talk about RTX scalability and our software releases. So these are like it says up there, these are really just ideas and suggestions. This is not one size fits all. I'm intending this as a starting point. If you want to achieve a baseline 60 FPS across generations of hardware with multiple visual targets, that's this might be a good way to start looking at it. When it comes to the technology itself, there's few actual limits that you have to worry about. The only hard limit as far as like what doesn't work where is frame generation. Frame gen requires 40 series, multi-frame gen requires 50 series, but aside from that, all of our technology works across all 4 generations of RTX hardware. So yeah, looking at the chart here, if you look at it from, there's 4 generations of RTX GPUs, and down the side are technology areas, not necessarily rendering. Most of it's rendering, but some of it's just like things we're trying to solve or improve. So stepping through this, if you look at direct lighting, for example, you could use ReSTIR DI across the whole stack. And note up here, I'm sort of saying high-end console is roughly equivalent to 20 series. Other hardware RT PC is roughly 30 series, but I mean, there's a lot of variation there, so that's just a starting point. But if you're just doing direct illumination, path trace direct illumination, you can use it across the whole stack. Now, you could replace this with megalights and still have compatibility at the indirect lighting level for ReSTIR GI and ReSTIR PT. That'll totally work. We're designing it so that it's your choice. You can do megalights, ReSTIR DI. It's going to depend on what features are important to you, what performance level are you looking at, things like that. And on the indirect lighting front, as I was saying, there's nothing to prevent you from using full path tracing all the way down on a 20 series. It's just that being realistic about it, it is an expensive effect. So you probably do need, more powerful hardware in order to do full path traced reflections. So at the lower end, you could design a project to use software lumen, and then from there, you go to hardware lumen, add in ReSTIR GI, and then at the very high end, you add, switch it to ReSTIR PT. Very similar set of considerations when it comes to reflections. It's a lot of the same stuff. It's just you'll notice that ReSTIR GI isn't noted here in the reflections thing because technically it's not making much of a reflection contribution. A little bit in rough reflections, but the real difference is when you activate ReSTIR PT because then you get full path traced reflections. Upscalers and denoisers have a lot of the same considerations. There's very little daylight between them. So if you're, at a very simple level, you can use DLSS super resolution, DLSS 4 super resolution, DLSS 4 ray reconstruction across all 4 generations. There's no restrictions there. The ORs here where it says OR NIS or OR NRD is if you're on non-RTX hardware. We give you other denoisers, other upscalers that you can use to fall back on if DLSS isn't available. Frame gen, like I said, 40 and 50 series only. There's some hardware tie-ins there. Reflex has no real restrictions. I learned this morning that Reflex actually is supported all the way back to 960. I didn't realize we went back that far. So, but it works on across all of our current gen hardware. And finally, with nanite geometry, no restrictions here as well. You can use mega geometry on a 20 series. Performance might be a consideration. Memory might be a consideration. So in that case, you could, users could use proxy meshes for lower end hardware, and then full nanite geometry for higher end hardware. And as with anything here, I mean, these can all be user preferences, right? So as you build out your project, let users decide what they want to turn on or off, depending on, what frame rate they're comfortable with. Okay, this QR code takes you to our NvRTX landing page. And we have RTXDI real-time path tracing out right now. We have DLSS 4 in NvRTX out now, but like I said, it's also a plugin and released as experimental, RTX Mega Geometry. So that should be out. You should also be able to find the Zorah example project as well as Amusement Park. And for both of them, compiled builds as well as project files. So please dive into them, check them out, take them apart, learn from them, ask us questions, et cetera, et cetera. Okay, that's it. This is our support email, nvrtxsupport@nvidia.com. And if you have any questions, please come up to the microphone. Thank you.
Hi. I work a lot with Lumen, and one of the things that's hitting us is virtual shadow maps.
Yes.
Of course, there are asset considerations and stuff. You indicated that RTXDI is available in your branch, but not as a plugin.
Correct.
I'm wondering how, whatever you presented today, is it easy enough to mod into the engine without taking your plugin. RTXDI specifically.
Yeah, no, I can explain that better. Yeah, the reason why, so why is DLSS a plugin
Yeah.
and RTXDI not? We would like everything to be a plugin if possible.
Okay.
That's our goal, is to always make things pluginizable or mainline it. That's happened with a couple of technologies, like Reflex has been mainlined. So you don't need to pull out anything for that. It's just, if you're working with Unreal 5, Reflex is built into it, along with a few other NVIDIA technologies. But RTXDI is not a plugin because it's too complicated. It touches on many things. It modifies light attributes. It changes the nature of several ray traced effects and so forth. So the plugin architecture does not currently allow us to make it a plugin. It would also be a very large plugin. It's very complicated code. So yeah, it's not realistic at the moment, but like I said, plugins are always our goal, and engine integrations are always our goal. We want to, our last step, the last thing we want to do is NvRTX, because we realize that's the most difficult way for you to get the software, probably. Right. You'd prefer a plugin, so that's what we'd prefer to do.
Right.
Yeah.
But RTXDI is fully compatible with Lumen, kind of.
Yes.
All right.
Yes.
Thank you.
Yep.
Hi, I have a question.
Oh, please step forward so we can hear.
Can you hear me?
Yeah.
Okay. Yeah, I have a question about ReSTIR PT. So I saw in the table scalability table, it shows that the ReSTIR PT only recommended for RTX 50 series, but not any of the previous generation. So can you comment more on why it's only recommended for the RTX 50 series, or is it any hardware improvement on the RTX 50 that the previous generation doesn't have? Is it like the new RT core or new shader or the more memory bandwidth on the?
So you were in the round table?
No, the scalability table you just show in your slides that shows that the ReSTIR PT, the ReSTIR path tracing is only recommended for RTX 50 series, but not any previous generation.
Oh, yeah. That's really just there's no hardware restriction there. ReSTIR PT runs anywhere on any hardware, ray tracing hardware. That would technically include even like a high-end PS5, right? But then the question is performance. So I'm making both. Like if you want to maintain 60 FPS, I wouldn't recommend putting full path tracing on low-end hardware. I'm just being realistic about it. But there's no restriction, and especially if that's not your goal, right? Like, let's say you're doing a real-time cinematic, and all you want to do is maintain 24 FPS. It's probably doable on lower-end hardware than I indicated. Yeah.
Okay, thank you.
You're welcome.
Hi, just a quick question regarding how does RTXDI compare with Megalights? Like, what are the performance differences and what are the quality differences? Are there any trade-offs that we should be aware of?
Yeah, there are many. I mean, okay, so there are things that they share in common and things where they're different. Where they're in common is very high light counts, right? And they share the same requirement. They both require hardware ray tracing. Past that, they get pretty different, and they have slightly different goals, I would say. RTXDI's goal is path-traced quality lighting, so it aims for, simulated photorealism as its major goal. I don't think that's this is where I could get in trouble. I'm not trying to speak for Epic. I don't want to do that. But I think they showed it more in the context of, like, we can achieve 1,000 lights on a PS5. So that's one way to work with it, is you could enable both in the project, and you could use, because Megalights, it doesn't have as many features as RTXDI. It doesn't do translucent shadow casting lights. It doesn't do Niagara shadow casting lights. It doesn't do those sorts of things. another thing I didn't have time for in this, path traced hair, where that's coming up. We don't have that out yet, but it's coming. And that'll be yet another feature for RTXDI. So fully path traced hair. So yeah, if any of those things are important to you, you'd probably want to use RTXDI if you need those features or you feel like they're valuable to you. But Megalights, it's probably designed for broader, maybe higher performance at a minimum spec. But you can have the project use both. When with NvRTX 5.5, like I said, you can enable both in the project and then just switch from one to the other. You can even make it a user preference. So the user could choose, do I want to use Megalights? Do I want to use RTXDI? And go that way. Yeah, so we aim for a lot of flexibility with this.
Thank you.
You're welcome. Cool. Okay. Thank you, everybody.